Hi everyone. In this session, we will look into a rectangular patch antenna design, modeling and simulation, in which we will model the antenna. We will define an excitation port, and later we are going to configure the simulation setup before simulating and analyzing the results. The simulated performance parameter should meet the design requirements set earlier. Note that we are not going to create feeding or simulating the feeding network together with the antenna, as this session will only involve single antenna element design. Let's review the structure of a microstrip antenna that has been shown in the previous video, resonant antenna. So in general, a microstrip antenna should consist of ground plane and also a radiating patch together with substrate. In this case, both the ground plane and the radiating patch is made up from copper, whereas the substrate is made up from taconic material. Let's begin with our CST modeling and simulation. Start with a new template. Select microwaves and RF optical. Choose antenna. Next, planar. Next, time domain solver. Next, make sure the units declared here are correct. Millimeter for dimension, gigahertz for frequency, and nanosecond for time. Next, we're going to design this antenna to operate at 3.4 GHz and monitor its performances at 3.4 GHz. So let's set our minimum frequency around 3 GHz and maximum frequency around 3.8 GHz. And let's monitor the E field, H field, and far field. Note that there are 3 monitoring points here, which is from 3 GHz, 3.4 GHz, and 3.8 GHz. For each targeted frequency, the E field, H field, and far field will be simulated. Select Next. If you're okay with this template name, antenna planar, click Finish. You can also rename this. Once done, it will bring you to this window. Let's maximize this. On the left corner is the menu. In the center here is where you will design, where you will model your antenna. The Progress tab will be mentioned here. And there are schematic point of this antenna, point of view, and also 3-dimensional point of view. In this case, we are going to do this in 3-dimensional. So there are a number of ribbons here. From home, whereby you can set up this setup simulation, the solver, choice of solver, modeling, simulation, post-processing. You can analyze the results after the simulation, and also the viewing options. Let's begin by declaring the material that we use in this antenna, that will be used in this antenna design, which is 2 items. For the radiating patch and for the ground will be the copper, and for the substrate it will be Taconic 35, which has the permittivity of 3.5. To do so, we can load this material from the library. CST has a number of materials that are available. So let's begin with copper. There are 2 types of copper. In this case, we are going to use copper annealed. Load. We'll repeat the same for the substrate, in which it will be a Taconic material. Taconic RF35 lossy. Click Load. You can double check this under this material folder. Taconic and copper are being currently added, together with the PEC and vacuum, which is available by default. Once this is done, we are going to start with ground plate. Select Break. Click Escape. Let's rename this as ground with the following dimension. negative 45, 45, 0, 60, negative 0.018, Z maximum as 0, and the material should be copper. Let's preview it. This looks okay. Click OK. Next, we'll proceed with the substrate layer. So in this case, I'm going to click F on my keyboard. It will automatically choose the function of face. In this case, I'll use the surface of this ground. Double click and extrude. I'm going to rename this as substrate. Height will be 1.52. And the material will now be Taconic RF35, the substrate material. You can preview this and it seems okay. I'm going to click OK. So now I have two structures here, the ground as well as the substrate. So the next phase is to proceed with the feet as well as the patch design. To design the feet, first I'm going to choose the middle segment of this edge. I'm going to press M on my keyboard and I'm going to select the middle point of this edge. Going to shift my WCS coordinate system to this point. Once done, I'm going to choose break, escape, going to rename this as feet with the following dimension: negative 15.2, negative 11.8, V minimum as 0, V maximum as 16.5, W minimum as 0, W maximum as 0.018. The material now should be copper. I'm going to preview this design and it should be there. So I'm going to click OK. So the next phase is to create a patch. So I'm going to choose break, escape, and rename this as patch. U minimum as negative 30.1, maximum as negative 8, V minimum is 16.5, V maximum as 49.5, W minimum 0, W maximum as 0.018. Material is the same, copper. So let's preview this. Yes, this should be in this position. So I'm going to click OK. So now I've completed my design with a patch, a feet structure, substrate, and also ground. The second stage is now to declare the excitation port. To do so, I'm going to zoom into the feet structure and I'm going to choose the surface of this feet structure, in which I'm going to click F on my keyboard and select this face. Then we will choose the available macros, in which in this case is the solver macro, ports, calculate port extension coefficient. So let's double check this one. The width of the feet is 3.4, height is 1.52, and the permittivity that is being declared earlier with our substrate material Taconic is 3.5. These are correct. And the suggested K would be 6.15. Once this is confirmed, click Construct Port from Pick Face. Close. So now we have completed this antenna modeling. From the components, which are the feet, ground, patch and substrate, as well as the ports. You're having here one port. Now this is being done. Next is to choose or to set up the solver. There are numbers of solver available in CST MWS. For this case, I'm going to choose time domain solver. Double click here, you will see these settings. And for this simulation, negative 40 accuracy, negative 40 decibel accuracy is acceptable. Then I'm going to click start. Note here the progress of the simulation is being shown in this window. %50 in progress with the simulation. Now the simulation has been completed. You click through under these messages. You can see that the ZY matrices has been successfully calculated, as well as the VSWR. There are a number of other parameters calculation has been shown here as well. So once this is done, let's go to check its impedance. Go to port modes and choose port 1, look at the E port. As you can see here, the mode type is quasi TEM and the line impedance is 48.8, which is near to our targeted 50 ohm impedance. So this results is acceptable. The next phase is to review, to analyze our one-dimensional results. We will start with port signals. As you can see here, the red markers or the red simulation is for the input, whereas the green is for the output. The signals of output and input are oscillating and slowly decaying to zero, which means that by this time the antenna is resonant, is operating. Secondly is to have a look at this S parameter. The targeted frequency is for this antenna to operate is at 3.4 GHz. So at this point, okay, let's choose axis marker. At this point, 3.4 GHz, the S parameters is -19, and the cutoff acceptable S parameter for antenna simulation is -10. So we can say that at 3.4 GHz, the antenna is operating and resonating. We can calculate the bandwidth of this antenna by determining the lower bound frequency at -10 dB, which is more or less around 3.35 GHz, and the upper bound frequency is around 3.43 GHz. Next is to review the power of this antenna. At the excitation port 1, there is only one excitation port that is available here. Let's move this marker at 3.4 GHz. Which is more or less around this, this point. Let me shift here. As you can see here, at 3.4 GHz, most of the power is being radiated. The power accepted point. Power accepted is at nearly its highest point, at 3.4 GHz. And at this point, the losses in metals and dielectrics are very minimal. The loss in metal is around 0.012 loss power watt in watt, whereas the loss which is due to dielectric is also significantly small, 0.03 watt. Hence, this is showing that the accepted power is radiated away from the patch antenna. Only a small portion is lost in terms of dielectric loss as well as metal loss. Next is to have a look on two-dimensional results. So we will start with E field. Let's monitor its E field. Let's choose at 3.4 GHz. Choose here as contour and choose smart scaling. So what we can do here is that we can animate this, and as you can see here, the electric field that is being radiated by this antenna. You can also do the same and evaluate the same for the H field, which is perpendicular to the E field just now. And we can also monitor the surface current. So in this case, as you can see here, the surface current happens at the edge, which causes the phenomenon of fringing effect, which leads to the tips of designing microstrip antennas. The ground plane must be wider than the patch design to counter this fringing effect. Next is to evaluate the far field results. In this case, let's have a look on its far field simulation results at 3.4 GHz. We can see here this antenna is having a unidirectional radiation profile pointing at the z-axis, zenith. We can evaluate this in terms of two-dimensional plot, theta versus phi, as well as in terms polar plot. You can see here the unidirectional radiation profile.